Hello folks, this video covers 11.5 and 11.6. We're going to squeeze 2 in 1 here because they're so closely related to one another. So here we go. We're gonna cover common logs first. And common logs are kind of exactly what it sounds like. Basically we have a common log, and you can shorthand this if you'd like. Common log is when no base is written. When no base is written, it is understood that the base is 10. So this is very similar to radicals, right? Like we know that we could have the cubed root of x and we could have the 7th root of x. But when we have a radical with nothing, we in the math world assume that that means a square root. It's very similar to that. If I just give you, so let's say for example, if I just say the log of a and I fail to write a subscript there, then it is understood in the math world that this is equivalent to log base 10 of a. So base 10 is technically the common log. So common log, that's the key there. Base is 10. And so if that's the case, let's talk about different types of logs with a common base of 10. So for instance, let's talk about the log of 1,000. When you think about, so it's understood that there's a small 10 here. If I asked you what this was equivalent to, we can change this to exponential form, which would be 10 to the x power equals 1,000. And then you'd say, okay, well, this is 10 to the x power. That must equal 10 to the, and then you have to figure out 10 to the what power is 1,000, which is the number of zeros, right, which is cubed. Therefore, x is equal to 3. So essentially what we're going to do each time is just that. Figure out 10 to the what power gives us that number on the inside. So the log of 1,000 is 3 since 10 to the 3rd power is 1,000. The log of 100 is 2 since the common log is 10 to the 2nd power is 100. And I should have written these a little bit closer together. The log of 10 must be 1 since 10 to the 1st power is 10. So you see the pattern here, right? But we're going to keep going. We're going to get through the threshold of 0. The log of 1 equals 0 since 10 to the 0 power, anything to the 0 power is 1. And we're going to keep going. The log of 0.1, if you're not good at the whole like decimals thing with exponents, remember that 0.1 is the same thing as 1 over 10. So this would be -1, since 10 to the negative 1st power is 0.1, or 1/10. The log of 0.01, 1/100th, is -2, since 10 to the negative 2nd power is 0.01, or if you prefer to think of it as 1/100th. The other thing too is think back to science when you do your scientific notation. When you have like a number 4.37 times 10 to the negative 5th power, that means you take your decimal and you move it that amount, right? So 10 to the negative 2nd power would be 10, and then I move my decimal, well, it'd be 1. Well, I didn't do 10 times something to the negative 2nd power. You move your decimal 2 places from where it is. And because it's negative, we know it's going to be smaller than 1. Let's do a couple more. Log of 0.001. This will be the last one. This is equivalent to 1/1000th, and it would be -3 since 10 to the negative 3rd power is 0.001, or 1 over 1,000, however you want to think about it. So this chart is going to be helpful to you. Again, I want to remind you, you're going to have a calculator portion on your test and a non-calculator portion on your test. You're going to have to do some of these log calculations using these breakdowns, if you will, with the small calculator, which does not have log capabilities. So in general, with your common log, in general, the log of x equals y implies that 10 to the y power equals x. And again, in general, log of 10 to the m power is equal to m, implies, or since, if our base is 10, that's the same thing as 10 to the m power equals 10 to the m power. So this is the big takeaway for common logs. Just understanding that base is 10, even if it is not written, and then when you switch it to exponential form, you write it with those bases of 10. So let's do a couple of examples. Again, these are going to be sans calculator. Number 1 is going to be, given the log of 7 is approximately, well, we'll say equal to 0.8451. No, I'm not going to say equal to, that's a lie. It's approximately 0.8451. Evaluate the following. So we're going to do a couple of different ones. So I want you to estimate the log of 7 million, given that the log of 7 is 0.8451. So what we're going to do is use some of this strategy that we did up here in this big old chart. And it's basically, okay, can we rewrite the number 7 million using 10 as, a base? And the answer is yes, absolutely. Basically, the log of 7 million can be rewritten as the log of 1 million times 7. And then using our logarithmic properties that we talked about earlier this week, when we're multiplying two numbers on the inside, we could break them up into two logs by separating them. So this is the same thing as the log of 1 million plus the log of 7. Now, the log of 1 million can be rewritten if you think about what we did up here, like when we had the log of 1,000. When we had the log of 1,000, we could basically rewrite that number as an exponent. So this is the same thing as the log of 10 to the, it's got 6 zeros for million, 10 to the 6th power plus, oops, this went away, the log of 7. Now you know what the log of 7 is already because they gave it to us in the problem. So now you say, okay, I know that the log of 10 to the 6th power is 6 because that's using this fact right here. The log of 10 to anything, if it's a common log, is just equal to whatever the exponent is. So this one's going to be 6 plus, we know the log of 7 is approximately 0.8451. So then when you add these two together, we have approximated the log of 7 million as about 6.8451. So let's do another one because this is really easy once you get the hang of what's going on. So let's do log of 0.0007. If you want to think of it this way, this would be 7 over 10,000 instead. Well, I'm sorry, 1 over 70,000 rather. In decimal form, you want to break this up into two logs, one having just the 7 and the other number being the rest. So we say, okay, this is the same thing as the log of 0.0001 times 7. And then using our logarithmic property, we're going to break these up into two separate logs. This is the same thing as the log of 0.0001 plus the log of 7. And again, notice I'm not saying base 10. It's just understood that we're dealing with base 10 now. Okay, log of 0.0001 is the same thing. If I wrote that as an exponent and I move the decimal 1, 2, 3, 4 times, this would be the same thing as the log of 10 to the negative 4th power plus the log of 7. And then, again, using this rule up here, the log of 10 to the negative 4th power is just negative 4. And then the log of 7 is given in the problem, approximately 0.8451. And then this is something you can calculate using your little 4-function calculator. This will be approximately negative 3.1, nope. Looking at my wrong numbers here. Negative, oh, it was 3.1549. So that's how you can approximate logs, by breaking up the number on the inside using, something as a base of 10. Now, you can straight up calculate stuff in your calculator. So if you don't have your graphing calculator, go ahead and grab that real quick. I could also ask you a question simply to approximate the log of 5. And using your calculator, if you look along the left side, the button's all the way on the left, there's a button that legit just says log. So if you type that button, then you literally type in the log of 5 and you hit enter. If I ask you to approximate that, typically in this section, anytime you do end up rounding, you need to round to the nearest thousandth. Okay, so the log of 5 would be, well, I guess we could go one more because it's got one more nice decimal there. Well, no, we'll keep it to the nearest thousandth. Okay, so if it's 0.69897 to the nearest thousandth would be this 9 here, but since this is 7, we would round that up, but rounding that up is going to cause the 8 to round up. So we will say, okay, this is about 0.699 for the log of 5. So that's just straight up typing it into your calculator. Your calculator understands base 10. Okay, so the other thing that we're going to have is this rule that's called the change of base rule. And it allows us to change any base of a logarithm that we want. The change of base rule says if a, b, and n are positive integers, and neither a nor b can equal 1 in order for this to be true. So if a, b, and n are positive integers, and a is not equal to 1, nor is b equal to 1, then the following is true. The log base a of n, so just any type of logarithmic expression, is equal to log base b of n over the log base b of a. So this is another big takeaway for today, the change of base formula. And it's really, really quite simple. In other words, if I gave you the log base, so number 3, I'd say log base 9 of 1043, and I wanted you to estimate this. If you had a calculator, or your calculator doesn't have properties other than base 10, some do, and some of yours might, which we can definitely talk about how to find that and how to enter in bases other than 10. But your basic graphing calculators don't have the capabilities of doing so. So log base 9 of 1043, if I follow this equation, that equation says it doesn't really matter what b is as long as b is not 1. So essentially I can make my base anything. So let's make this base 10. Let me do log base 10 of n is the big number, 1043, divided by log base 10, bases have to match, of a, which a is the original base, right? N is the original big number. So log base 10 of 9. And then, of course, we don't have to write base 10. So essentially, you're going to be able to skip this step altogether when you do change of base. You don't have to write that part at all. When you get here, you say, oh, this is the same thing as log of 1043 divided by log of 9. And then you can type that into the calculator exactly as you see it. Log of 1043 divided by log of 9. Now, be careful. My calculator, you have to close the parentheses after you enter in 1043. So just be careful to see what software your calculator has and whether or not it opens parentheses or not. And if you round this to the nearest thousandth, you get about 3.1630. Okay, this next idea, we're not going to use it a ton, but I definitely do want you to be made aware of it in case it comes up again later. But basically, sometimes the log of a value, or the log of x, we'll say, is known to have a value of a, but x is still unknown. And in that case, we say that x is called the anti-logarithm of a. Anti-logarithms. Logarithms. I think that's how we spell it. Yep. Okay, and basically what that is if I have log of x is equal to a, again, an understood base 10 here, then this implies that x is equal to the anti-log of a. So if you think about it in terms of inverse operations, this would be like taking the anti-log, or the inverse is essentially what it is, of both sides. If I take it of the left side, then it leaves me with x. If I take it of the right side, then I'm left with the anti-log of a. So remember, common logs have base 10, right? So if I have common logs have base 10. So if I have the anti-log of 10 to the 0 power, basically what's going on is in your calculator, your anti-log is going to be if you hit the second and then the log button. And you're going to notice it's 10 to a certain power. Well, yeah, I didn't want to say 0. It's just 10 to some power. That's what the anti-log is. Let me put anti-log is 10 to the something power. So let's do an example. I want you to find or calculate the anti-log of negative 0.06. And it's super easy. You just use your calculator. If you hit second log, then it's like taking the anti-log of the anti-log would be the log, essentially. Or just doing that inverse, base 10 would be the exponent of base 10 to the negative 0.06 power, which would be approximately 0.871. And there you have it. Now, the main thing that we're going to be dealing with exponents and logs and common logs and natural logs is solving. Okay, so this next section I think is probably going to be the most important for us. So if I ask you to solve something, previous to today, you might not exactly know what to do. So if I give you the equation 6 to the 3x power equals 81, you might try to say, okay, well, I have an exponent. I know when I see an exponent, in order to like get rid of it, I take the root of whatever it may be. And that's not really possible because you can't take the 3x root of this and then make things go away. So what you have to remember is that the inverse of exponentials are logs. The inverse of exponentials are logs. So if you take the log of both sides, then what happens is this. The log of 6 to the 3x power is equal to the log of 81. Now, if you think back again to our properties of exponent rules that we talked about the other day, if you have the log of a number and it has to an exponent, then the rule is that this exponent comes out front as multiplication. You multiply them. So this is the same thing as 3x times the log of 6 is equal to the log of 81. So if I want to isolate x, you could do this all in one, but you risk typing something in incorrectly. So I would just do it in two. If I'm trying to isolate x, I'm going to go ahead and divide both sides by the log of 6. That leaves me with 3x is equal to the log of 81 divided by the log of 6 is approximately 2.4526 if I was to write some more. Don't retype that in the calculator. So at this next step, when you divide both sides by 3 in your calculator, just keep that long decimal in there and then hit divided by 3, and then you'll get your value for x, which is approximately 0.8175. So that's how you solve. Let's do another example like this. Number 6. Again, this is another big takeaway for today. Inverse of exponentials are logs. That's what you use when you solve. So let's solve. 5 to the x power equals 4 to the x plus 3 power. So again, if I have exponents, if my variables are in exponents, in order to get them down, I need to take the log of both sides. So I'm going to take the log of 5 to the x is equal to the log of 4 to the x plus 3. And then again, the exponential property, I need to make this a little bit more exponent, there we go. The exponential property says if you have the log of a number that, and then that is to an exponent, then the rule is that these exponents actually drop out front and multiply in front of the log. So this would be x times the log of 5. And then here you got to be careful. This x plus 3 needs to remain together in a set of parentheses times the log of 4. Now, you can't do like what you did over here and start dividing to try to isolate x, because right now your x's are not isolated. So you don't want to make this any messier by calculating logs of numbers, because that's just going to give us crazy decimals. So what I want you to do is actually distribute this log of 4 on the right side to the x and the 3. So then that gives us x times the log of 5 equals x times the log of 4 plus 3 times the log of 4. And then we can say, okay, well, this term no longer has an x. This one does. So let me move all my terms that do have an x to the other side. So I'm going to subtract x times the log of 4 from both sides, which then gets me to x times the log of 5 minus x times the log of 4 is equal to 3 times the log of 4. And then we can isolate x by saying, okay, let's factor it out of both of these terms. So if I factor out an x, I'm left with the log of 5 minus the log of 4 equals 3 times the log of 4. And now that x has been pulled out, if I want to actually solve for it, I'm going to divide both sides by this big expression, the log of 5 minus the log of 4. So 3 log of 4 divided by log of 5 minus the log of 4. And you got to be careful. I'm going to take one more step to rewrite, what exactly should be typing in your calculator. 3 log of 4 all divided by, in parentheses, log of 5 minus log of 4. So your calculator should look, again, I don't know if your calculator does stacked fractions or if it opens parentheses or not, but you do have to add in your own parentheses around this term that's in the denominator to let your calculator know that that's all in the bottom. Okay, I think solving is pretty simple. There's not a ton to it. You just have to know your logarithm properties. I think entering it in the calculator is where people tend to make their mistakes if you're not careful. So hopefully you've got an opportunity to enter that in by now to see what this would be. In doing so, you should get that x is approximately 18.6377. And that's how you use logarithms as inverses of exponentials to solve.